They
I
cannot.
informed in groups, sir, but some people still join.
It is only 38 people, right? Not beyond that. Okay, it's up to them what they want to have. So the next class that we are going to study, yeah, let me record it. Very good morning, students. Today the topic that we want to discuss is analysis of experimental data. So far, what we have seen is a basic understanding of the terminology that we generally utilize or use in measurements. Then the basic elements, how do we study, all of that we have studied in the previous class. And then we have also looked at different kinds of classification of systems, measurement systems, and how the differentiation of different inputs will be done, and when different inputs are given to different systems, how they will behave. what can we expect if a particular input is given to a particular ordered system. So those things we have so far studied. The next very important thing is, so we have a measurement system and then we have taken certain readings. How do we analyze them? So from any measurement system, you give an input, automatically it will show an output. How do you ensure that the output coming out of the system is nearer to the input value? How do you do that? Whether the instrument over a period of time, any instrument over a period of time will be subjected to wear and tear, okay, and therefore there may be some error that comes into the picture. So how do you know that whether this measurement system is precise, accurate or not? So as we have discussed in our previous classes, accuracy is one thing and precision is another thing. Accuracy is how close the measured value is to the measured. Okay, so for the input, how much closer the output is. That is what you are calling it as the accuracy. In another sense, it may be called as an error also. The other thing is the precision, where even though you are getting some deviation from the true value, whether I am able to repeat the same thing when I have done the same experiment multiple times, whether I am very close to that deviation or not. The output is scattered all around differently, or it is scattered only at a particular small region, in a very small region. That tells you the efficacy or efficiency of the particular measurement system. I hope you are unclear. So now, for doing that, we have to understand how do we analyze the data. So whatever the data that we get, how do we look into it to ensure that there should not be any deviation, or whatever the deviation that comes into the measurement, we should be able to understand that this is the error that has crept in. So that is what we are going to look into this particular class. Okay, so now first we will start with the types of errors, and then how do we solve with each kind of an error. Okay, the broad classification of errors we will see, and how do we deal with a particular kind of an error. So whenever we get some experimental data, we need to always provide or perform some kind of analysis. So what is that analysis includes? It includes the determination of error, which is the deviation of the measurement to the measured value, how much precise the repeatability, and whether this measurements are valid for agreement for others also to follow. you have done an experiment, if someone comes back and builds a similar experimental setup and does the same experiment, whether he will be able to get very close to those values or not. That is the validation. So the validity of the experimental data becomes also very, very important. So how much error we can expect as an experimentalist, you have to explain. Okay, so the experimentalist, as an experimentalist, you should always know the validity of the data. A quality experimentalist will always spend his time in validating his own data. He will not rush. Suppose if you get some idea, you have performed some experiment, you should not jump to conclusions and try to publish or try to come out and say that I have got a valid results and all. That's wrong. You have to first validate the results that you have got. Validation means you are kind of doing an analysis to find the correctness of the data. Whether the data is repeatable or not, you have to look at it. Whether it makes sense, whether it follows the basic principles or it is contradicting the basic physical principles that we understand. So all these things will come into picture. If you got a experimental reading which is not at all following, for example, yesterday we have in our lab experiment, we have two things. One is the constant speed test which you are going to do today, and then there is a motoring test. Okay, so what happens is in a constant speed test, we run the engine and we try to find out the frictional power. Okay, so we run the engine means what? We are providing some fuel and the fuel gets combusted, and when it combusts, it gives a lot of heat, and because of the heat, the piston gets slightly expanded, very slightly. So to move freely within the cylinder, it has to overcome some friction. So therefore, we have some frictional force. The other test to find out the frictional force is the motoring test, where we rotate the shaft. We are not burning the fuel or anything. We are just rotating the shaft by means of an electric motor. You give an electric motor and you will rotate the motor. And by rotating the motor, what you are trying to do is you are actually moving the engine and trying to find out the frictional power. But here, there is no combustion that is taking place within the cylinder, no temperature, and therefore no expansion of the metal, and therefore the frictional forces are supposed to be lesser. But when we perform the experiment, we are getting the motoring test frictional force is greater than for the constant speed test where we burn the fuel. So this is a general contradiction to what we know so far. So we should be, as an experimentalist, I should not jump to conclusions looking at the data. That is not my strong point in a nutshell. Okay, you have to stick. You have to look at whether these results makes any sense, whether they be able to follow the physical principles that we know, whether it is logical or not. That is what you have to seek or look at as an experimentalist. Take any experiment, regardless of how much care you take, you always will have some errors that comes into picture. So that means you always will have some deviation from the true value. That is for sure. So that is what the deviation, whatever we are getting, we generally term it as errors. Okay, so therefore, as an experimentalist, you know that error will come, definitely. As an experimentalist, you have to be certain. A particular observation, maybe how much uncertainty, how much deviation you can expect out of a reading. Okay, and you have to have a consistent way to specify the uncertainty in analytical form. Have you understood what I want to say? So you are doing a particular set of multi measurements, and then you have a set of observations, and you have to be, as an experimentalist, you should have the analysis in such a way that you can say that out of all these readings may fall within this range from the true value. Okay, so this is the range, maximum range. It will not go out of this range. And suddenly, secondly, you should be able to specify that in some form of analytical means, in some mathematical form, you should be able to communicate to others. Okay, that is the task of a good experimentalist. As we have seen, error means deviation from the true value. These are two very same terms. So deviation means deviation of the measured value from the true value is nothing but your error. Okay, so we are actually classifying the errors into two types. Okay, one is the systematic error, and then the second one is the random error. Okay, basic errors are classified into two types. One is systematic or fixed errors. Second one is random errors. Let us look at what are systematic error and what is a random error. Systematic errors means these errors that are not determined by chance but are introduced by an inaccuracy inherent in the system, they are also called as fixed or bias error. So you got a new system, okay, a new measurement system. In the first 2 or 3 years, it will give very close readings. Okay, it will perform very neatly, and then the technician will not maintain it properly. He will not oil it properly. He will not lubricate it properly. So therefore, there are certain moving elements into it. They keep on rubbing to each other, and over a period of time, if you are not maintaining it properly, lubricating it properly, then dry friction will happen, and therefore a gap will form in between the mating parts or moving parts. And because of that, what happens? Because of that, slowly you have an error that is consistent over a period of time. So that error will be consistent. It will not vary. Whenever, because of that, if you do for a x1 reading, it is supposed to give y1, but it may give y1 dash. Okay, so that means some deviation will be there in the output. Again, for if you take z, you are supposed to get m, and then you will get m dash, for example. So y dash and m dash are the actual deviations we are getting. So we are getting some error which is consistent. Even if you repeat it, it will come. So that kind of errors we call it as. That's why the name itself you are getting as fixed or bias error, because they are inherent in the system. Because of improper maintenance, because of wear and tear, these terms are because of the inefficiency of the person who is actually taking measurements. All of this will, because if a person X does the experiment, he is of some height. Suppose he is 6 feet and the experimental system is around 3 feet from the ground level. He has to bend and look at, so always there will be some parallax error. And then the other person will come who is around 4 feet. He'll be looking at that in a proper way. Okay, so there may be some error which comes in, but whenever the 6 feet high person does the experiment, he will always look out from the same distance. So in general, he will get a kind of an error. So these kind of errors which are consistent, and these are because of because they are inbuilt within the system, are inherent in the system, are what we call systematic errors. Clear? And random errors are measurements that lead to measurable values being inconsistent. So when repeated measures of constant attribute or quantity are taken. So what do you mean by that? So random errors means you never know why these errors are coming. You have no clue. So for example, one of the parameter may be influenced by humidity and you don't know it. Suppose you are doing the experiment in Chennai, it will be different, and when you bring it to Warangal, it may be different. And when you do that same experiment in Hyderabad, it may be different. But you are unaware that it is influenced by humidity. Okay, so that kind of an error we call it as random error. Okay, so I'm just saying an example that humidity, but sometimes there may be a certain reason, but you will not be able to pick it out. What could be the reason for this error? So such errors, which we cannot determine by our logic, by our careful observation, something. So such errors we call it as random. They come in and go randomly. One time when you do, it will come. There may be a flow. For example, in the morning time there is a good wind, and suddenly you are doing an experiment where flow measurement you are doing. So how quickly the velocity is, and there is a flow that is backing it up. We don't know, the surrounding air is moving, and therefore some error will come. After certain time the air has stopped and you are doing the same experiment, you are getting a slightly lower value for the given same inputs. the same standard conditions, and same person who is taking the measurements, but the flow of air surrounding it may be changed. You don't know because that effect is very slow. So initially one value will come, second time when you do, it will give another value. So such kind of errors, we call it as random. We don't know why those errors has come into picture. Whereas systematic errors, we have a logical understanding of why it is happening, and they're fixed. Wherever you do, the same error will come. Such errors, we call it as systematic errors. So any doubts in this, you can ask now. Is it clear? Right. Now, how do we solve these systematic errors? So that is the question. Now, systematic errors are predictable and typically constant or proportional to the true value. As I have told you, they are in general constant or proportional to the true value. So if the deviation, whatever we are getting, it is consistent. So such errors we call it as systematic errors. So therefore, we can always find out the reason why this may be happening. So by careful observation or by taking proper care in the maintenance of the system and all that, we can always identify, and they can be eliminated by doing suitable calibration. I'm talking suitable calibration. Okay, so systematic errors, why they will be caused, sir? What is the reason why it will cause? There may be imperfect calibration of measurement instrument. So as I told you, the systematic errors can be eliminated by one of the process, what we call it as a calibration. I will tell you what is calibration in detail. So one of the thing is, if you are not doing your calibration properly, then because of the imperfect calibration of the measurement instrument, this will come into picture. Second, imperfect method of observation. As I told you, you have to take the measurement without parallax error. You have to be very, very careful while taking the measurement also. You cannot be you cannot take the readings without any proper care. However you are taking the first reading, you should ensure that the same methodology will be followed to take the second reading also. Okay, suppose if a needle is vibrating over a range, in the first for a first input it is vibrating over a range 1 to 1.5, then obviously what you will do, you will take the average 1.25. And then again, if it is for the second input, it is vibrating over 2 to 2.5, you should be always taking the average of this 2.25. You cannot say that it is close to 2.4, I will take 2.4. So the principle based on which you are actually taking the measurement, it has to be consistent. That is the meaning of imperfect method of observation. So if you are not following the same methodology followed to take your observations, so then also it will come into picture. Third one, as I told you, interference of the environment with the measurement process. As I told you, these are basically humidity, maybe temperature, maybe velocity. So these are all the external conditions which are having an impact on the measurement process. Therefore, it is always better to repeat an experiment within the same condition. Suppose we have done in our PhD some experiments. So whenever my professor want to repeat the experiments, I have conducted that at night 2 o'clock, because the humidity levels will be lesser at night 2 compared to in the morning. Therefore, I performed the experiments at 1, and my experimental results are very prone to be affected by around 1% error will come if my experiments are prone to high humidities. So in order to repeat the same experiment, I used to go and perform the same experiment every night at 2 o'clock. Okay, likewise, I done that repetition for another 20 days. So it is that much important. You should not forget that the environmental or the external effects will always have a say in the measurement process. So, and because of that also, you will always have this kind of systematic errors. But what is the good thing about this error? This error will always take a predictable direction. Whether it goes on increasing, when you increasing the input, the error may keep on going on increasing by a particular proportion. So that is a good thing. If it is in following a particular direction, it is easy to find out. It is easy to measure the deviation. If it is following a zigzag path or it is random in nature, how do you ensure what can be the deviation? It will become very, very complex for doing a measurement for that purpose. Okay, so the best thing is systematic errors are inherent because of the system, and they are due to the imperfect calibration, perfect method of observation, environmental effects, and all of this. But the best thing is you can always, since it follows a predictable direction, you can always able to measure the error with basic methodologies. Okay, so now let us go to the calibration process. How do we eliminate this kind of a thing? Okay, let us look at that particular part. So here, what I'm trying to do, you can, I think you can see here, I have drawn a graph where I'm giving an input and there is an output. Is there any message? Should I go back and see? There was some sound.
Hello, sir.
Yeah.
I wanted to ask one question, sir.
Yeah, Abhilash only, yeah?
No, sir, Amarnath.
Amarnath, tell me, Amarnath.
Sir, just now you mentioned about the environmental errors. Mostly, sir, in our campus, in odd semesters, we do experiments in rainy or like somewhat humid climates.
Correct.
And in even semester, we do it half in some in winter, half in and summer, and means some experiments in summer. So why don't we like change and check whether our errors and all these things are consistent?
See, the problem is how much the effect of the environment on your experiments. That is more important, no? So if it is having a 1% error, do you care? If it's not very precise or accurate one. See, whatever all the experiments that you are performing in our labs, they are only basically for making you understand the for giving you a feel of a physical experimentation, right? So I don't think whatever the thermal and other things that you are doing in your experiments at the undergrad level, they are very much affected by the environment. That's why that doesn't matter. But suppose if you are using some thermal, so for example, as I told you, there are certain paints. Okay, so those paints, they give color. They are used to measure force. How they measure force? When we touch or apply some force, it gives a color, for example. And such precise things, they are also dependent on humidity. Suppose, and whenever you apply force and humidity varies, without, even though your pressure force is constant, it gives a different value, different color. They are very much affected by the environmental conditions. In such cases, you have to be very, very careful. See, in our IC engines, how does that affect? Your reading output will not be that high. And another thing, you are not comparing the previous values, even though you got some 10% error, let us say. What we are looking at is, every time you does an experiment, you are getting a mechanical efficiency of an IC engine around 25 to 35%, for example. 25 to 35, anything is fine, no? 28%, nobody say that you are wrong. You have got 24% in the while writing your record, but now nobody will say that. So these experiments are different compared to the experiments that I'm seeing. These are academic experiments which can have some error, and there is a range for this error, and that is always accepted. That's why we don't keep on, we don't say a particular value. Even you have in heat transfer one experiment, what we call as Stephen-Boltzmann constant. Okay, so the value of Stephen-Boltzmann constant is a constant value, 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. And you try to get the same value by having an experimental setup, the radiation principle, that is a constant value. So whenever radiation happens, that value has to come like that. So by knowing the voltage, current, and then the temperatures of all the including paths, we try to estimate that. But when you try to do that, every time it will not get the same. It will be close to 5.1 or 5.4, 5.5, and still you will get a marks for it. So my point is very simple. If you go and perform experiments in your PG or in your PhD, you should be wary of these things. But as an academic, as for the day-to-day academic understanding when you are performing experiments, you need not worry too much about it. Okay, so another question. Am I clear, Amarnath? I hope I am clear.
Yes, sir.
Yeah. So Abhilash Reddy Gaddam, he has asked another question. Doesn't environmental errors comes under random errors? Sometimes, if you don't know the reason, then environmental errors becomes random errors. But if you know, then it will become systematic errors. For example, if you have a consistent velocity, for example, as in the same experiment. So by when you vary the inputs also, your deviation is always consistent, right? It may not come down. Okay, if there is a continuous flow of air. Suppose if there is on and off air and it is it is influencing the output. If the air is not continuous, sometimes it is blowing and sometimes it's completely come to a stall. It is not moving. Then this will create a random error. In that case, it becomes a random error. It's not in continuous nature. You understand the basic difference is like this. I will tell you. The basic difference here is if the sorry, if it is kind of increasing like this, like this, like this, like this, like this, you don't have any issue, whether it may be slope or it may be in. But instead like this, if it goes for your understanding, I'm just showing. For just imagine that this kind of randomness is there in your input to output relation. How do you find the error? Okay, sometimes for this input it is giving this value, for the second output it has increased to that, and the third input it has lowered to this value. Okay, so this kind of nature will not allow you to estimate the error. So this randomness, if you are finding in the results, in the deviations, then it is a random error. Okay. Now, systematic errors, as I told you, how do you find out the systematic errors? Suppose you have 10 kg of input and the instrument has given 11 kg. The second one is, suppose you have given 30 and it showed 32 kg. And then you have put 80 kg, it gave 83 kg. And then you know whatever your value is 90, 100, and you've got some 104, for example. See how much it is increasing here, 1 kg from 10, it has increased by 1. When it comes to here, it has increased by 2. When it comes to here, it has increased by 3. When it comes to here, it increased by 4. Okay, by a value of 4. So the error is continuously increasing. But what I can do is, these values I should, in general, what is the system? You don't know the input. You are giving some unknown input, and through the measurement system, you are measuring. So you will get the output. The question is whether the output is actually measuring properly the input or not. So for that, what I am doing is a kind of a process which we call it as a calibration process, where I know the input values which are standard. So the input values, I am very sure of the input values what I am giving. There is no error. Even the error is there, it's a very minute error. So always we have to perform the calibration with the help of a known, precise or accurate input values. So now I am very sure about the 10 kg, 30 kg, 80 kg, 100 kg. They are very, very accurate, precise. Okay. Now, whatever output from the measurement system, I am getting 11 kg, 32 kg, 83, 104. So over a period of time, my measurement system has got some error like this. Okay, it got some deviated values from the input value. Now, I have drawn a curve, okay, and making all the points, and then with the help of this curve we will get by means of regression analysis. What I am trying to do is I have discrete values, right? 10, 30, 80, 100. What happened to 20, 25, 27, 33, 35, 38? What are those values? I don't know. I have taken some discrete values and I'm trying to create a continuous function for that. So what I'm trying to do is I'm trying to connect all these points, and so that I'm trying to fit a curve for that. So the fitting of the curve will be done by a method called regression analysis is what we call. So by means of regression analysis, earlier they have to do a mathematical thing and all. Now it is very, very easy. You can do that by means of an Excel file very comfortably, very smoothly. So with the help of a regression analysis, you are trying to fit a curve, best fit for the data. So that means it passes almost through most of the points. I am trying to fit a curve, and that curve I am trying to give in the form of a mathematical equation y equal to mx plus c. For example, it may be a second order, it may be a fourth order, it may be a logarithmic, it may be an exponential function, whatever. So I'm trying to find out the closest. Okay, so now that mathematical equation y equivalent to mx plus c, for example, it is in this form. Now for every input, for any x, it gives you y. Okay, so that means now you know what from the system, you know what is your y, right? You will get y. From that you will find out x. Now x equal to y minus c by m, correct? Y minus c by m is what your x is. So you will now from the system, if you get 11 kg, if you put 11 kg here, you already got the slope of the curve and you know the intercept, and therefore your x will be exactly 10. Okay, so by doing this, you are able to get back to the input properly. Even though your output reading is this, your calibration equation will help you to get the accurate value. Right. So even though there is a systematic error, you are able to eliminate that error by doing suitable calibration. So what is the major requirement for a suitable or a proper calibration? For a proper calibration, you should be knowing the precise input values to test with it, or a standard instrument. For example, if you are measuring a flow, okay, so you have a flow measuring device or velocity measuring device like hot wire anemometer, we will say. You know that is the most accurate one. So you have a hot wire measuring instrument. But what happens is the principle is you are having a fine thin wire for which you are keep on giving current, all right, and the flow, what happens when flow takes place over it, what happens, it cools down the wire. Therefore when the temperature is reduced, your resistance will vary. Therefore for a given current, you are having an output differently. So to maintain this bridge circuit properly, you will vary the current accordingly. Whatever reduction in the resistance, you will try to put more amount of or less amount of current. So the deviation in the current is proportional to the flow. Therefore, you are linking those two and you are able to measure the flow of the or velocity of the flow. So this is the principle. Now what happens? Suppose some dust particles are settled on the thin fine wire, for example. And when you are flowing the air, this smallest part, because it's a thin wire and it's supposed to be a very thin cylinder, because of the presence of these small dust particles, the flow velocity will vary. So the resistance may not change accordingly. So in that case, you are always having error with that. So therefore, whenever you are using a measurement system, a precise or a very precise measurement system, you have to calibrate it first. Now, how do you calibrate that? You have a measurement system which gives a flow. Is that sufficient? Is that sufficient for calibrating? You have a system, measurement system, which can measure the flow. So this is the, let us say this is the measurement system that can give the flow. Is that sufficient? Through this orifice, it is coming out, the flow is coming out, let us say. So you have a fan over here, you have a current over here, and then it is running and rotating this blower, and therefore air is coming out through this. Is that sufficient? That is my question. You have a hot wire anemometer over here. Okay. Please somebody answer, guys. I mean, I'm not expecting correct answers. Nobody will laugh at you because they also don't know, right? Let us understand that this is the hardware anemometer. Okay. So now the flow is coming in this direction. That's what I'm saying. Now, when the flow is coming and hitting the wire, whatever for this, I should know what this measures. This gives an output. What is the requirement? There is a fan that is rotating, and therefore we are controlling the air, and that is coming and hitting. Will this be sufficient? That is what my simple question is. Is anybody there in the class or not? Hello?
I think, sir, we should know like what would be the errors, because we can't say how it is performing.
What would be the
Errors, like in measuring it.
now? How do you know error? First of all, you should know how do you know error here. I have only this particular system, right? I have only this blower here, which actually sucks in air and pushes the air through this orifice. So what I want to say is there should be a measurement system here which actually knows very accurately how much air is pumping through it. Okay, so that is the requirement here. So when this system which tells us very accurately with how much velocity I am sending the air by operating a valve or something, if I have this valve by 20, it will give only 20 liters per second of, or 20 meters per second of air. If it is kept 30, it is accurately sending 30 meters per second of air. Likewise, I should have a standard measurement system, and to there I have to take my experimental setup or by my device and then test it. So now here 20 meters per second is coming out, I know, because it is a standard one, and this I believe in this system. So what is the output from this system? That is 21 meters per second. For example, 42 meters per second or 45 meters per second. Likewise, I try to provide a curve like this, a calibration curve like this, and from that I will fit a curve, put an equation, and this equation will help me to get the, and now I am taking this and I'm keeping somewhere where I am measuring the flow. Now I don't know the actual flow that is coming out, but I will use this output, whatever is coming, and I will give it as an input to this equation to get the actual input. So true input of that. So that is the use of a calibration system. I hope I'm not repeating this thing. So were you able to understand? I've only started 4 slides only.
Yes, sir, we understood it.
Clear? So
yes,
now,
sir.
So that is what we call a calibration system, and it is very, very important whenever you are doing an experiment as your PG student or a PhD student in your doctoral studies. First thing for any experiments, even for a thermocouple, you use thermocouple for measuring your temperatures, right? And temperature over the surface of the plate and all, you use a thermocouple. But for making sure that your thermocouple is giving a correct value, you have hot water. We call it as a hot water bath, wherein the temperature, will be a heater and it is controlled properly, and therefore the temperature of the heater, the hot water, is measured properly. Whatever the input you are giving, the current input that you are giving by resistor heater, it gets heated up, and then whatever the temperature you are measuring through that, the hot water measurement is always correct value. So now in that hot water bath, for a 30 degrees temperature, when you heat it to 30 degrees temperature, that is precise. You are taking this thermocouple and putting into that, and with the help of a data acquisition system, you will measure the thermocouple temperature. Okay, the thermocouple temperature, how it measures? There are two junctions, two dissimilar metals. You know that principle, Seebeck effect and Peltier effect. So the Seebeck effect will tell you that when two dissimilar materials are joined together at two different junctions and their temperatures are different, EMF is produced. So this side you are having a very high temperature, that side you are not having a high temperature. So because of this delta T, a voltage will form, and with the data acquisition system, you are actually referring this voltage to a temperature. So whatever change in the temperature, you are measuring the temperature, and the temperature through the data acquisition system will give you the temperature sensed by the thermocouple. So that is your output. You know the precise input and you know the precise output. Likewise, you make the similar kind of a thing, and then you know the equation. So this expression, the calibration equation, you will give as an input to the data acquisition system, and it will record. Now, whenever you want to measure any system, so the same thermocouple, when you put it over here, it gives an output. Internally, the data acquisition system will calculate by putting that value into this equation and finally displays the X value. So that is how the instrumentation will be done, the experimentation will be done. So all I want to focus on this is how do we eliminate the systematic errors, and that's why I spend so much of time on that. So this is very, very important as an experimentalist for you to know this particular thing.
Sir, like how can we believe in the measuring system? Like if you're saying it is a standard of measuring system and it won't, like we believe in them, but it may have some error, right, sir? So
but they are made of, so that's why they are called standard systems. For example, you have a first order system, primary measurements, we know primary standards. If you say that, sir, how do I know primary standards, means we cannot answer. So they are made, they are manufactured very precisely by the instrument, and they are called as calibrating instruments. If you are finding a hard calibration bar, they will give, those people will give you the specifications. For that 0.01 degrees variation, plus or minus 0.01 degrees variation. That means 20 degrees means 20.01 or 19.99 is the maximum variation that it will have, not beyond that.
okay.
So that is what those instruments, you have to select it properly. So those instruments are to be standardized. They are standardized machines, then they will be used where across the world as standard instruments. Only those things you will buy and always keep on repeating or calibrating your experiment. You cannot take randomly something and measure. It's not that. Okay, you should have that. As I told you, that's why I gave you an example. Thermocouple means you should have a hot water bath. Hot water bath is basically costs around from 80,000 to 1 lakh for a good one, Sulabo. So that is standard. Everywhere, any experimental paper, if you say, the thermocouples are generally compared with that. Likewise, okay, there are 20,000 also, you will get a hot water bath. But over a period of time, how it behaves, nobody knows. But Julabo, for this, most of the people will believe that, so you can always use it. Likewise. Okay, I'm just giving an example. Now, how do we estimate the, so again, random methods, you never know how this will come. They will be present at some time and there will not be, they will give absolutely true value. They keep on varying. Sometimes the value will be higher than the actual input. Sometimes the value will be lower than actual input. So you never know. There will be a fluctuation in the reading. They are inherently unpredictable fluctuations. For example, a simple example I will tell you. So now what you are trying to do is, you in your childhood you might have played a game like with stones. You will be throwing the stones, and therefore there are 7 or 8 stones, and you keep on how close you are. You try to hit his stone, and then that game you might have played. We have a stone, and then we keep on hitting each other as well. First one will throw, other one will try to hit that. If he misses, the other one will again try to hit that. Likewise. So for every hit, he has to give some amount to him. Likewise, we used to play. For example, now if there is certain measurement, some distance, and you have to accurately throw this stone to that point, like a golf point kind of a thing, you have one area, and you are trying to put every time the stone to that particular point. Sometimes the point you will be exactly putting your stone to the point. Sometimes you may overcross it. Sometimes it may fall before the actual point. So it is random in nature. No, similarly, your random errors will also be there. It may be sometimes higher than the actual thing. Sometimes it may be lower than the actual value. But there is a fluctuation. There is a scattered data that you will get, isn't it? So now, how do we solve it, sir? This kind of a problem, we don't have any other measure except doing some statistical analysis. Okay, we will only have statistical analysis to find out this kind of to solve this kind of errors. Okay, which will creep into the measurements without our knowledge and behaves irregularly. Okay, so how do you get these random errors out, sir? This can be done by doing multiple measurements. So many readings you will take, and by doing the statistical analysis, you will try to what we say, reduce the uncertainty or reduce the error. We will try to reduce that by using this method. Okay, sir, why can't we use the same method for systematic errors? Because systematic error, as I told you, it always follows in the same. Whether if it gives in one direction, that means it always, if first reading goes over the reading, second reading also will be going in above the reading only. It will not fall down below. If it is falling down below, that means a random error is also present. Okay, so that is how the systematic and random errors will behave. The difference is systematic errors always follows in one particular direction, whereas a random error may take a zigzag path. It may not follow any particular direction. Okay, so systematic error, if you are able to observe, it can be eliminated. If you know that because of this mating friction, if it is happening, you can always eliminate. Sorry, you have a class at 11? Do you have a class at 11?
No, sir. At 11:30 we'll have.
Okay, so can I continue for another 10 minutes? Is it okay, right?
Yes.
For gas dynamics people, it is okay. Like for others, I don't know.
Yeah. Is it okay for gas dynamics people? Another 10 minutes. I will not take much of it. One simple example and I'll close.
Yes, sir. Yes, sir. Continue, sir.
Yeah. So the one of the simplest example for the systematic error, you have this current, this voltage, which is specified by 100 plus or minus 2 voltage. So this may be plus or minus, this may be the summation of, for example, you take it as a deviation that is happening. Okay, and simply current, you also have 0.2 amperes. One of the simplest way to calculate the power, the basic formula is power equal to E into I. Okay, so now in this certain cases, you know the deviation, how much it is coming around, which is a component of both systematic and what we call, it may be a reason by means of systematic error and a random error. Because of that, this may be happening and this may also be happening because of that, but somehow you are able to find out this kind of an error, how much it is. And then how do you estimate the final output for the power? Okay, for the power, how much deviation you will have? How do you do that? In general, you will take the maximum and the minimum power values, and from that deviation, you will try to say that this may be the error. Okay, so now you will calculate P max with 100 plus 2 into 10 plus 0.2. In one direction, if the errors are above, the maximum error is 1040.4 volts. For what? 1000, right? 100 into 10. It should be the error, but because of these errors, you are getting 1040.4. Similarly, you are taking the other way around, where 100 minus 2 into 10 minus 0.2. You are taking negative value, the other extreme, the lowest value. It may show around 960.4 watts. For 1000 watts, the power may be, suppose the power should come 1000 watts, but it is showing 960.4 watts or 1040.4 watts. So this is the range because of the deviations I'm getting in the power. So therefore, the error will be in between 4 plus or plus 4.04% to minus 3. When it goes lesser than this, it will be minus 3.96%. And if it is higher, I mean, the range is in between this. Plus, it may be plus 4.04 0.04% or minus 3.96%. That's how you will calculate when you are having an equation with these deviations. Okay. So now this is what I'm talking about, the uncertainty over here. Let us not get into, first let me finish the uncertainty part, statistical analysis part, and then I think it would be better if I talk about this uncertainty analysis. So I will stop this at this point of time. Sorry, it was raining here, so I had to come from home, so I took 10 minutes of time for me. I mean, I was delayed the class by 10 minutes. I'm really sorry for that. And tomorrow I will take around 11 o'clock. Okay, our class will be at 11 o'clock. Is that fine for you guys? I mean, every Saturday Sir is asking, don't think like that. So I hope you are okay with 11 o'clock class.
Okay, sir.
This is fine. Others? No problem, right?
No, sir, it's fine.
Yeah. So any doubts in this class so far? Those people will stay back. Others, they can leave. And thank you for attending the class. And Kalyan, please inform the class. The class strength is very low. Then you may have to take the attendance. Okay. It's only 47,
Yes,
including me. Yeah. Please take the attendance. Keep a track of the attendance. And finally, I have to fill the attendance sheet and all. Just keep the track of the attendance of the people. Okay. Let's see what they, because you cannot allow the people to miss the classes, and sometimes if it is required, that's fine, but not every time. Okay. So that is it. Any questions? I would be happy to answer. And another thing related to the lab, you asked for some time. I increased the time, but please don't keep on asking that. It's a simple thing. Another thing is next week also we are getting a holiday, I think, correct? Friday, next Friday. You are missing the lab. Already we missed 2 labs, right? We are yeah, so that will be Vinayaka Chavati. If you are doing, then it will be second lab, right? You are missing 2 labs. And finally, it may be upon you. So it will. So can we finish the second and third experiment today itself, so that you will be along with the A section?
Yes, sir.
Kalyan, not only you, others can answer. If nobody is there, then I should talk with Kalyan.
Sir, only 2-3 people will answer like we are okay, but we can't say about others, right, sir?
That is true, but if according to you, 3 or people who say yes, it means yes.
Yeah, it's fine for me, I guess.
Yeah, because you will be lagged otherwise. However, if you're not doing now, you may be asked to do it last hour at least.
Yes, sir. Your words are
That is
true.
also a pressure, right? So why to go keep pressure, because these 2 are continuous experiments. Anyhow, I have to talk with the professors. I thought of yesterday itself that this may be a problem for you, so that if you are in line with the other section, that would be good. So I thought of this. So we will talk with the professor. I'll talk with the professor, and around 2 o'clock, if it's possible, we will try to finish both the experiments today itself. Okay. And I will give you for record. I can give you some time. That's not a problem. Okay. I will not rush you to write the record at all, but explanation wise, it's a continuation thing. Same experiment, but tests are different to find out the friction. Okay.
Yes.
I hope you have no questions in the this particular class. Do you have any questions in the lab? You can ask me. If I know, I will try to answer you. Regarding lab, any questions? Fine. Can I take that you don't have any questions about the lab also? Right. So then please take care. And tomorrow is a very important class, and please don't miss the class. It's not for exam and all. You can always read and learn. And I think these are all my experiences that I'm trying to tell you. It's not available in the textbook. So please do come to the class tomorrow. Do attend the class tomorrow. So that will be an interesting, according to me. I don't know. You have to tell me at the last whether you find interesting or not. You have to tell me at the last. Let's see. So please take care of yourself, and I'll take a leave from you if you have no doubts at all. Right. Thank you. Have a great day. Bye.
Thank you.
Thank you, sir.
Thank you, sir.
Yeah. Thank you.